All right, let's talk about something that sounds, well, incredibly intimidating: complexity theory. But what if I told you the core idea behind it all is something you see happen every single time you make a cup of tea? Yeah, we're going to make this surprisingly simple. Let's dive in.
I want to start with this quote because honestly, it just cuts right through the noise. The reputation that complexity theory has for being this impossible, brain-breaking subject, it's mostly just bad branding. It's a communication problem. And this is the real secret. The actual logic behind it is something you already get intuitively. It's the mountain of academic jargon and the super formal language that makes it feel like you need a PhD just to start. So we're just going to push all of that to the side for a bit and focus on the one core idea.
And here it is. This is the whole game. This is the one question that the entire field is trying to answer. What happens when you have a bunch of things following simple rules, but there are a lot of them? Everything from weather patterns to stock market crashes to traffic jams, it all comes back to this. So to understand this, we don't need a supercomputer or a particle accelerator. Nope, we just need to go into the kitchen. Because our main guide for this whole explainer is going to be the simple, everyday act of boiling water. You know this process like the back of your hand, right? You start with water in a kettle. It's stable. It's just sitting there. Then you add energy. You turn on the stove. The water heats up until it hits a critical point, 100 degrees Celsius. And then wham, a total phase change. It's not just hot water anymore. It's boiling. You get these brand new behaviors: bubbles, steam. And then when you turn the heat off, the energy input stops, and the system eventually cools back down to a stable state.
Now, believe it or not, in that simple process, you've just witnessed all the key features of complex systems. I mean, think about it. Once the water's boiling, you can't just unboil it instantly. The state it's in depends on what just happened. That's called path dependence. The boiling itself, that's an emergent behavior. It's a whole new kind of thing that you couldn't have predicted just by looking at a single cold water molecule.
Okay, so here's the decoder ring. This is how we translate the kitchen into the classroom. What we intuitively call temperature is what a scientist calls a control parameter. The boiling point, that's a bifurcation point, or a critical threshold. And the bubbling and the steam, that wild new state, those are called emergent attractors. See? The scary language is really just a formal, precise way of describing what's happening in your kettle. All right, you ready? Because now we're going to make the big leap. We're going to take this simple pattern, add energy, hit a threshold, create a new state, and we're going to apply it to huge, messy, complicated systems. This is where it gets really interesting. The key, the absolute trick, is to realize that temperature is just a metaphor. It's a stand-in for any driving variable, any kind of energy or pressure that's being pumped into a system, pushing it towards a tipping point. Once you get that, this analogy becomes a kind of universal tool. So let's try it. System, the global climate. In this case, the temperature is, well, it's literal heat in the atmosphere and oceans. And what's the boiling? It's the whole system hitting critical thresholds and flipping into a new phase, one defined by cascading tipping points like melting ice caps, shifting ocean currents, and really extreme weather. What about the economy? Well, here the temperature isn't heat, it's something more abstract, like capital flow or speculative energy. When too much of that heat gets pumped into one part of the market, the system starts to boil. It forms a bubble. And just like steam from a kettle, those bubbles have to release that pressure, so they burst, leading to a crash. And yes, this pattern even applies to society itself. Here, the temperature could be something like social tension, or inequality, or just collective outrage. When that tension builds and finally hits a critical point, the system boils over. And that boiling looks like mass protests, revolutions, or these huge sudden shifts in social norms. Okay, so really getting this requires a pretty deep shift in how we look at the world. It's asking us to stop seeing a collection of static things, of objects, and start seeing a universe of dynamic flows and processes. Now, this can feel a little weird and unnatural at first, and there's a good reason for that. Our brains are built to take shortcuts. We only get to see a tiny little snapshot of reality at any given moment. So to make sense of it all, we compress these long, continuous, flowing processes into what we perceive as stable, separate objects. It's a really useful illusion, but it's still an illusion. This example is just perfect.
When you look at a plastic bag, your brain says, object, plastic bag. Simple. But if you're thinking in processes, you see something different. You see a temporary, stable arrangement of hydrocarbons in a much, much longer process, a process of slowly breaking down and becoming microplastics that will then flow through entire ecosystems for centuries. The object is just a quick snapshot. The process is the reality. To put it another way, what our brain labels an object is really just a temporarily stable pattern. It's an attractor state that manages to hold its shape just long enough for us to give it a name. But underneath that illusion of stability, the particles are always flowing.
Okay, so let's take a deep breath. We're about to take this logic to its absolute final conclusion. We've gone from the kitchen to the climate. Now we're zooming all the way out to the entire cosmos. And here's the biggest mind-bending idea of all. Complexity isn't just some neat tool we use to describe things in the universe. No, the universe is a complexity-generating engine. The cosmos itself is this vast, recursive, self-organizing process that creates complexity out of simplicity.
So, how does it do that? Well, the fancy term is ontological individuation, but all that really means is it's the process where distinct things, separate structures, emerge out of a perfectly uniform, boring state. It happens when that perfect symmetry breaks in one little spot, allowing something new to form. It's how the universe goes from being just potential to being something.
And we can literally see this exact process playing out over the history of the universe. It's a cascade of cosmic phase changes. It started with impossibly tiny quantum fluctuations that broke the perfect symmetry of the Big Bang. Then, during inflation, those microscopic breaks were stretched out to astronomical size. And those tiny, ancient asymmetries became the seeds for every single star and galaxy we see today.
So, there you have it, the entire story of the cosmos, told through the lens of complexity. You start with the quantum foam, that's your room temperature water, the state of pure potential. The tiny symmetry breaks are the first injection of energy. Feedback loops then amplify those seeds, and through a whole series of phase changes, the nested, self-organized, beautiful universe we live in emerges.
And when you see it this way, an ancient phrase like as above, so below suddenly stops sounding so mystical, doesn't it? It's almost a literal description of the physics of a universe that's built on these repeating self-similar patterns. The same core logic that boils the water in your kettle is the logic that forges galaxies in the cosmos.
And that's really the thought I want to leave you with. Now that you have this lens, now that you can start to see the processes behind the objects, what things in your own world, in your job, your relationships, your society, what things that you always thought were static, stable objects are actually dynamic, flowing processes, maybe even getting ready for their next phase change?